Welcome to section 6.1. We're going to begin looking at a new family of functions in this section. This chapter is going to revolve heavily around them, so make sure that you refer often to this definition. So if you're consulting the notes on the first page of this section, section 6.1, you'll see our definition. So an exponential function is any function of the form b to the x. This is the basic exponential function, so f of x, where x is any real number, so x could be anything from negative to positive infinity, and b is also a real number greater than 0 and not equal to 1. Now there's a discussion at the bottom of that page of why exactly we make these restrictions. So for one thing, if we had y equals 0 to the x, that would be a pretty boring function most of the time, because 0 squared is 0, 0 cubed is 0. Any x value that we plug in is going to give us 0, unless the x value is negative, right? 0 to the negative second would be 1 over 0 squared. So remember those properties of exponents. I recommend you review those if this trick that we tried here was out of left field. Alright, well that's 1 over 0, which is undefined. So a bunch of weird stuff happens with this function. Most of the time it evaluates to 0, and then some of the time it evaluates as being undefined. So we exclude the possibility that b, the base of the exponential function, is 0. Alright, now the reason that we exclude the possibility of the base being 1, well, if we had y equals 1 to the x, well, 1 to the first would be 1, 1 to the second would also be 1, 1 to the negative fifth would be 1 over 1 to the fifth, which would be 1 over 1, which would be 1. So no matter what we plug in, 1 to the 0, that's also 1, for a variety of reasons, we always get 1. So this function is perfectly valid. This is a nice enough function, but we don't include it in the family of exponential functions because this one is really just linear, right? We always get the same output regardless of the input. And we have already seen functions that behave that way. Y equals 1, that would be a horizontal line. So this gives us the same y values no matter what we plug in. So this is not, as we would say, an exponential function. Now something even weirder happens if we look at a negative base. So if we look at y equals negative 2 to the x, well, I'll come up with an actual table for what's going on with this one. So if we have x and y equals negative 2 to the x, if we plug in 0, we would get negative 2 to the 0, which is 1. Anything to the 0, except for 0 itself, gives us 1. If we raise negative 2 to the first, then we just get negative 2. Alright, no problem there. If we square negative 2, then we're going to get positive 4. So we have a positive output, then a negative output, then a positive output. Let's go one further. If we cube negative 2, notice that I am plugging x into the exponent, right? Our variable is in the exponent now, no longer down on the ground floor of our expression. Well, if I cube negative 2, I'm going to get negative 8. So we see how this kind of flip-flops from negative to positive. What if we were to plug in x equals 1/2? Well, that would give us negative 2 to the half power. Well, the half power, that's another way of saying the square root of negative 2. And the square root of negative 2 is the square root of positive 2 times I. So sometimes we get positive outputs, sometimes we get negative outputs, and sometimes we get complex outputs. So this function is just very strange. It is a function. There are fields that may study this function. I've never worked with it myself, but it certainly can be evaluated using all these inputs. We see what outputs we end up with. Some of them are complex, so that's a little odd. But it's not going to behave generally the same way that the other exponential functions do. Alright, so we don't like negative bases, we don't like the base to be 0, and when the base is 1, things are just a little boring. Okay, so our definition, the types of functions that we're going to be looking at in this section are always going to look something like this. So for example, y equals 2 to the x, or y equals 1/5 to the x, or y equals 7.86 to the x. These are all valid exponential functions. The base, 2, 1/5, 7.86. The exponent, our variable. So this is quite different from polynomial functions, as we've seen before. So y equals 2 to the x, and y equals x squared are very different functions, right? I would plug my independent variable into the exponent of the first function, and I would plug my independent variable into the base of the square function. So let's look at how those differ from each other. So we've got our table set up here. We're going to look at what our outputs do when we plug them into these two different functions. 2 to the x, the exponential, and x squared, the quadratic. Well, if we plug 0 in for x into this first function, we get 2 to the 0, which is 1. If we plug 1 in, we get 2 to the first, which is 2. Now we're going to be using those properties of exponents quite a lot, especially here early in this section, to figure out what these functions even look like. So 2 squared would be 4, 2 cubed would be 8. If we go in the negative direction, if we plug in x equals -1, 2 to the negative first, that negative will flip things for us. We get 1 over 2 to the first, which is 1/2. Similarly, 2 to the negative second, that'll flip things for us, 1 over 2 squared, which is 1/4. And if we continue in that direction, our values will get half as big each time. So notice, for each increase in x, our previous value gets doubled, right? We add 1 to x, and we double y. We add 1 to x, then we go from 4 to 8, double y. Alright, that works in reverse as well. If we subtract 1 from x, if we go backwards, then our output gets half as big. If we subtract 1 from x, our output gets half as big. Subtract 1, half as big. Subtract 1, continuing in the negative direction, and we get half as big. Subtract 1, half as big. So that really gets at the heart of the exponential function. For every step that we take horizontally, our function doubles. Now that can lead to what's called an exponential explosion. Imagine you have a population of rabbits, and you have 2 rabbits to start with, and they have 2 baby rabbits. They double the population. And then the population doubles again, so now you've got 8 rabbits, and then 16. And if you're familiar with powers of 2, after that you'll have 32, then 64, and then 128, and then 256. And we're only a few months into this, and already 2 rabbits have turned into 256. So that, as we'll see with the graph, type of behavior can get very large very quickly. Now our exponential, on the other hand, if we plug in 0 and we square it, we get 0. If we plug in 1, we're squaring it and we get 1. If we plug in 2 and we square it, we get 4. Okay, and if we plug in 3 and we square it, we get 9. However, in the other direction, if we plug in -1 and we square it, we get 1. If we plug -2 in, we're squaring that, and we get 4. So our negative inputs deliver much larger outputs. And that's kind of another feature of the exponential. The negative inputs give us fractional, smaller and smaller fractions, because every time we step backwards in x, our y gets half as big. Now this question of getting half as big poses an interesting quandary. Can we ever get down to 0? So let's take a look at the graph and see if we can make sense of that. Okay, so first we'll plot our f of x. So when x equals 0, we determined that y was 1. So there's our y-intercept. When x was 1, our output was 2. When x was 2, our output was 4. And when x was 3, our output was 8. And if we went a little further, if 4 was our input, our output would be twice as high, up at 16. Okay, now going in the other direction, if we look at negative x values, when we plugged in -1, we got a half. -2 gave us a quarter. And if we kept going, -3 would give us an eighth, a 16th, a 32nd, a 64th. And we can keep going in that direction. You'd get smaller and smaller fractions. Every time we move to the left one, our y value will become half as large as the one before it. But we're never quite going to get to 0. So just like the graph of 1 over x, the graph of 2 to the x has what's called an asymptote along the x-axis. It gets closer and closer the further out we go horizontally, but it never quite gets there. So I can show this graph kind of approaching 0 and connect up all of our dots and assume this behavior is going to continue. This is based on a pattern. So there's 2 to the x. And we already know what x squared looks like. Passes through 0, 0, 1, 1, 2, 4, let's see, 3, 9 right there. If we kept going out a little bit further, if we take 4 and we square it, we get 16. So hit that point again. We take 5 squared, we get 25, right? So 16, 17, 18, 19, 20, 2, 3, 4, 5. Right about there. And in the other direction, -1, 1, -2, 4, -3, 9, and so on. So our parabola actually gets overtaken by the exponential function. So we get two very different shaped graphs based on these similar looking equations. So you want to make sure you keep straight what's your exponent and what's your base. Alright. Now the first graph that we came up with, 2 to the x, exhibits the shape that all exponential graphs will have. So if you consult the notes on the next page, you'll see a table outlining some points on 2 to the x, 3 to the x, and 4 to the x, along with the graphs of each of them. They're color-coded. And you'll see that 2 to the x grows, as we observed here, but 3 to the x grows a lot quicker the further out you go in x in the positive direction. And 4 to the x grows even faster. So each of those is an example of an exponential function with a base greater than 1. Now, as x increases, we're multiplying the previous value by that base. So, for 2 to the x, when x increases by 1, y doubles. For 3 to the x, when x increases by 1, y triples. So the next value is 3 times the previous value. You can see we go from 1 to 3 to 9 to 27. For 4 to the x, we quadruple the previous value. We go from 1 to 4 to 16 to 64. And that explains why our growth is so much quicker the larger the base. So the larger the base, the faster your function will grow. Now, on the other hand, we'll look at an exponential function whose base is not greater than 1, whose base is in that other possible part of the domain between 0 and 1. So if we plug in some x values and see what y values we get, the calculations with this type of base are a little bit more difficult, but you can always plug this into your calculator and have it do the work. Let's see what happens if we plug in 0. So 1/2 to the 0, well, we have a property of exponents that says that that is always 1. If we raise it to the first power, 1/2 to the first means 1/2. Okay. If we square it, 1/2 squared. Well, that would be 1 squared over 2 squared, so 1/4. And if we cube, we would get 1 over 2 cubed. In other words, 1 cubed over 2 cubed, or 1/8. So notice, as we increase x, the y value gets half as big. In other words, we're multiplying the previous y value by that base. Increase x, we're multiplying by 1/2 again. If we increase x, we multiply by 1/2 again. So that's what the exponential does. It multiplies by that value of the base over and over and over, whatever x tells you that many times. If we go in the negative direction, so 1/2 to the negative first, well, that negative will flip it for us, so 2 to the first, which is 2, right? Which is twice as big. So if we go in the opposite direction, our values get twice as big. So if we decrease x, we double y. If we decrease x, we double y. Decrease x, double y, and decrease x again, and we're doubling y. And if we keep going, -2, we're going to double y again and get 4. If we plug in -3, we'll double it again and get 8. Plug in -4, double it again, we'll get 16. And you can back that up by actually plugging in that x value and evaluating. So 1/2 to the -4th, that's 2 to the 4th, which is 16. And 1/2 to the -3rd, that's 2 cubed, which is 8. Alright, so our graph here, I'll have these little tick marks along the y-axis represent 1/2. So go up to 4, go up to 8 vertically. Alright, now we say that when x is 0, y is 1. So plot our y-intercept. When x is 1, y is 1/2. So 1/2. When x is 2, y is 1/4. 3 gives us 1/8. Notice we're getting closer and closer to 0 in this direction. 1/16 if we keep going, 1/32, and so on. Now if we go in the negative direction, -1 gave us an output of 2, -2 gave us an output of 4, -3, 8, -4, 16. We might not have room for all of these, but -1, 2, right there, -2, 4, -3, positive 8, negative 4, 16 might be up into the table. But we can connect these up. Our graph will exhibit this same basic shape, getting larger and larger as we go off to the left, getting smaller and smaller, closer and closer to 0 now as we go off to the right. Alrighty, so those are our two graphs, and I'll put 2 to the x back on here. So 2, 2, 4, 3, 8, negative 1, 1/2, negative 2 1/4, negative 3 1/8, and so on. So there's 2 to the x. And 1/2 to the x. Okay, so these are the basic shapes of our exponential functions in this section. We have two possibilities. Either our function's going to be growing, like 2 to the x, or it'll be, as we say, decaying, like 1/2 to the x. So notice that 2 to the x is always increasing. That is, as we read from left to right, it just gets bigger and bigger. On the other hand, 1/2 to the x is always decreasing. That is, as we read from left to right, it just gets lower and lower. Now, both of these graphs are 1-to-1 because they stick to whatever it is they're doing. If it's always increasing, it's 1-to-1. If it's always decreasing, it's 1-to-1. So later on, we're going to see what the inverse of this function looks like. If you are up on your graphing, you can probably make a guess as to the approximate shape of the inverse graph, but we'll define it a little more thoroughly than that in the next sections. Notice that both of these graphs pass through 0, 1. That's common to all basic exponential functions. Any function like this will contain 0, 1 as its y-intercept. And all of these functions have this asymptotic behavior. They gradually, eventually, approach that horizontal asymptote, the line that sort of bounds them from below, we might say. So refer to Theorem 6.1 on the next page of the Notes PDF for some details about these graphs. They have a domain of all real numbers. No matter what the base is, you can always plug in any x value. And as we said, they always contain 0, 1 as their y-intercept. Now another interesting thing, on 2 to the x we had this point 1, 2. Notice the relationship between the base and the y value. On the other graph, we had the point negative 1, 2. On the graph of 1/2 to the x, we observe the point 1, 1/2. So whenever you plug in 1 as the exponent, you're just going to get the base. So that's another very easy point for you to find on the graph. I recommend playing around with these. Try graphing a couple of exponential functions of your own devising. Maybe try graphing 5 to the x using a table of values like this. It's very easy to perform the calculations and then plot the points that you come up with. It's good practice, so give that a try. Now, once we're familiar with the shape of these graphs, remember if our base is greater than 1, we're going to have this increasing, upward sloping graph. If our base is less than 1, somewhere between 0 and 1, so any fraction in that range, our graph will be decreasing. Once we know the shape of one of these functions, we can start applying transformations to it. Alright, so I would like to use what we've learned so far to make some inferences about functions that may otherwise be a little strange. So first we have a function f of x equals 2/3 times 3/8 to the x. Now this function I need to recognize as a exponential function. It's not a basic exponential function because here out front I have some constant multiplier c. So we always call the base of the exponentiation b for the sake of the definition. So if our base b equals 3/8, is this function going to be increasing or decreasing? Well, I know because it's an exponential function that it's got to be one of those two. And I know that since the base 3/8 is less than 1, the graph is going to look something like 1/2 to the x. So this is a decreasing function. Alright. Now for part B, we're given a different function, g of x equals 1.7 to the negative x. Now this function is not in the form of a basic exponential function, right? Our basic exponentials have x as the exponent. Here I have negative x. So I can think of this as 1.7 to the negative first to the x. That's one of our properties of exponentials. Negative x is negative 1 times x, and a product in the exponent can be thought of as raising the base to one of those factors and then to the other. Alright, well, 1.7 to the negative first, that's 1 over 1.7 to the x. Now, 1 over 1.7, again, that number, we don't really need to know exactly what it is, but I recognize I'm dividing 1 by something larger than 1. So this is going to be a small number, smaller than 1. And so my function is again, in this case, decreasing. Okay, so we want to figure out what the base is. The base of the exponent will tell us everything we need to know about whether our graph is increasing or decreasing. Now for our next example, we're going to look at some transformations of one of our basic exponential graphs and determine what the graph will ultimately look like based on what we know about the starting graph and the transformations taking place. Now here's my function, f of x equals negative 3 to the x minus 1 being my exponent, minus 4. So I like to categorize things sometimes. So outside of the basic function, remember the basic function that we're basing this all off of is going to be, I think, 3 to the x. Okay, so outside of the base to the power, 3 to the x, we have a negative causing, remember what multiplying a function by a negative, this is negative 1 times 3 to the x minus 1, a vertical flip, alright. We also have a minus 4 shifting our graph vertically down 4 units. Now on the other hand, inside of 3 to the x, where is inside? Well, that's going to be where my variable would be. Normally I have 3 to the x. In this case, I have x minus 1. So inside of the function, we're replacing x with x minus 1, so that's going to shift the function horizontally, And since it's minus 1, we're going to shift in the positive direction 1 unit. So we're shifting to the right 1. We have a vertical flip across the x-axis. And we're going to shift everything down 4 units. Alright. Now our basic function, 3 to the x, has a base of 3, so this is going to be one of our increasing graphs. Normally we would have a y-intercept at 0, 1, and normally y equals 0, the x-axis would be our horizontal asymptote. I like to shorten that to HA. Alright, well if we flip our graph, my y-intercept will reflect down to 0, negative 1, but my horizontal asymptote is in the same place. My graph still approaches y equals 0 as we go off to the left. But when I shift my graph down 4 units, its horizontal asymptote will move with it and become y equals negative 4. And similarly, our our y-intercept will shift down 4 units to 0, negative 5. And finally, put that all together, the graph of my function. Here we have the x-axis, the y-axis, and our horizontal asymptote, 1, 2, 3, 4. I like to put that as a dotted line so that I know the boundary that my function is trapped by. 0, negative 5, our y-intercept. And the basic shape of our graph will be flipped over, reflected vertically. Now the only thing missing is that horizontal shift. So if I move my graph 1 unit to the right, my y-intercept is in the wrong place. So how would I find a y-intercept for a function that I'm not really sure what that point is? Well, let's see that on the next page. For right now, that y-intercept was actually incorrect. We took care of the vertical shift, but we forgot about the horizontal shift. Alright, so all of our fancy transformation tricks can help us come up with the graph, but they may not be as wonderfully helpful in finding that particular point we're interested in. So remember, to find a y-intercept, what do we want to do? We want to set x to 0. So f of 0 would be negative 3 to the 0 minus 1 minus 4. And now we can crunch that number. That's negative 3 to the negative first minus 4. Now, what should I do first? Should I apply the negative to 3, or should I apply the negative 1 power? Well, the order of operations says exponents first. So, negative is going to hang around, wait its turn, and the negative 1 exponent will flip the 3, and it'll become 1/3. So negative 3, or negative 1/3 minus 4. If we get a common denominator, that would be negative 1/3 minus 12 thirds. It looks like our result is negative 13 thirds, or negative 4 1/3. So our original thought, the y-intercept being 0, negative 5, would have been nice. That would be a nicer number. But it's actually 0, negative 13 over 3. So finding those y-intercepts looks exactly the same conceptually as it has through the entire course. The only new idea is in the execution, and actually calculating that y value. But you can definitely do it. If you remember those properties of exponents, you'll be absolutely fine in this section. Now, generally speaking, our basic exponential looks like f of x equals b to the x. But quite frequently in the wild, when we're actually working with these functions, we might see a less basic version, where we could have a constant multiplier. F of x equals c times b to the x. Alright, so we're multiplying b to the x by c, effectively stretching. And potentially flipping our graph. Alright, so let's take a look at a working backwards type of problem. So this function will have a y-intercept at 0, 1. That's always true. If we plug 0 in, no matter what the base, the result will give us 1. What's going on with f of x over here, the less basic version of the exponential? Well, its y-intercept will be at f of 0. In other words, if we plug 0 in, we would get c times b to the 0, and b to the 0 is 1. So we get c. So this has a y-intercept of 0, c. Okay, so the original y-intercept, if all we're doing is stretching our graph, is going to get stretched from a height of 1 up to a height of c. Makes sense, right? Multiply that y value by c, you're going to get c at the end. Alright, so here we have the graph of an exponential function. For one thing, we're told to find an exponential function fitting this graph. For another, this graph resembles an exponential function more than any other functions that we have seen thus far in the course. So I know that an equation for this function might look like f of x equals c times b to the x. This graph exhibits almost all of the features that our exponential, basic exponentials exhibit. It has a horizontal asymptote here along the x-axis. It grows exponentially, just like we would expect an exponential graph to grow. This is increasing, so we can infer that the base, whatever it turns out to be, will be greater than 1. Alright, but we actually have some points to work with. So remember that f of 0 equals 2, so f of 0 equals 2. Now f of 0, based on the structure of our function that we know about so far, would look like c times b to the 0, which would be c times 1, which would be c, so it looks as though c is equal to 2. Now, if you refer back to the previous page, we just came to that conclusion. If we stretch our function, our new y-intercept is going to be at a height of c. So c equals 2, because our y-intercept is 0, 2. Alright, so let's make a revision. Our function now can look like f of x equals 2 times b to the x. Alright. And what else is this function doing? Well, the only other thing I know about is the other point that it's passing through. In other words, this point must be a solution to this equation. So we'll plug in that point and then force b to satisfy the equation. So f of 2, that is 2 times b squared, must be equal to 20.48. Alright, now this equation, we can solve for b quite easily. This is a quadratic equation in b. If we divide both sides by 2, we get b squared equals 10.24. So b itself is the positive or negative square root of 10.24. Okay, well, b can't be two different things, so which one of these possibilities is correct? Well, the cool thing about exponentials is the base is always positive. So the base can't be negative. Base b must be the positive square root of 10.24. And we can plug that in now. This version of our function is out of date. We can say f of x equals 2 times the square root of 10.24 to the x. And I sometimes like to put parentheses around the basic exponential part of things so I can see what my constant is and what my actual base is. And I don't get mixed up about which part or which parts are being raised to the power. So that would be our function. And if you plug that into your grapher, let's bring out the graphing calculator. We'll type y equals 2 and the square root of 10.24, and we'll raise that, and this is where you need your caret button, to the x. And I'll adjust my window accordingly so that I can see around those 2 points. So I want to be able to see below and to the left of 0, 2, so I could go over to maybe -3 for the x-min and maybe -5 or -10 for the y-min. Just anything below the x-axis would be good. Then I want to be able to see to the right of 2 and above 20.48, so maybe I'll go over to 3 and up to 25. Alright, that should be a good viewing window. If you have your standard zoom, you can tell that the graph looks like an exponential, but it's a little hard to see the points that we're interested in. Alright, so our graph looks pretty solid. Let me go to the table and verify that the points that are supposed to lie on this graph actually do. So if I go to the table, my table is currently set up for auto with a starting point at 0 and a step every unit. So if we plug in 0, we see we get 2, so the point 0, 2 is good. And if we come down to x equals 2, we see that the output is 20.48. So that second point lies on the graph, and that is all that we were asked to accomplish. So our graph does what we want it to do. It's an exponential function, and that is all that we need. So the next topic is the exponential growth or decay model, which is sort of a generalization of what we've already seen. And that looks something like P of t, where P represents our population or our amount or the value of whatever it is that we're measuring, and T rather intuitively represents time. So the setup looks a lot like what we've already seen. We have P sub 0, which is a constant multiplier of the basic exponential part of this function. So that P sub 0 represents our initial amount, our initial value. And the reason for that is if we plug in 0, in other words, if time is 0, if we're just starting out, then we get P sub 0 times b to the 0, and that gives us P sub 0 times 1, which is itself P sub 0. In other words, the y-intercept, or the vertical intercept, of this sort of general model is 0, P naught, P sub 0. We call B, instead of calling it the base, we call this the growth or decay factor. The reason for that is that's what we're multiplying by each time we increment t. So if we're doubling, our growth factor would be 2. If we're tripling, our growth factor would be 3. If we're decaying, if we're getting half as much value for every increase in t, then this would be a decay model, and we would call it the decay factor, and b would be 1/2. So it's a growth model if b is greater than 1. It's a decay model if b is less than 1. And that kind of makes sense. If b is less than 1, our function would be decreasing and our graph would be falling. If b is greater than 1, then our function would be increasing and our graph would be rising. So let's take a look at one of these in action. Suppose we have a data set here representing a population or an amount over time. Here we're letting time be represented by x, or maybe x doesn't represent time. This is some other type of exponential situation. So the first thing we would like to do is determine, is this going to be a growth or decay model? So I would note that when we first start out, our amount is 34, and later, after 3 weeks or months or minutes or whatever x represents, our value has decreased down to less than 1, down to 0.87. So I would argue that this is a decay model. In other words, we know now that b is going to be less than 1. Now another easy datum to pick out from this information, from the table that we are given, is the initial value. Remember, the initial value is however much we have at time 0. So the initial value, p sub 0, is going to be 34. So we're on our way to being able to figure out the formula for this situation. To do that, we're going to need to figure out exactly how much our amount is growing or decaying every time period. So, what do we know so far? We know that p of x is going to look something like p sub 0 times b to the x, and we already know what p sub 0 is. Let's instead write this as p of x equals 34 times b to the x. Well then, if we plug 3 in for x, we would get 34 times b cubed, and that's supposed to be equal to 0.87. So we'll enforce that based on the second point that we're given, and then we can solve for b. So if I divide both sides by 34, I'll get b cubed equals 0.87 over 34. Now you can plug that into your calculator. I'm going to leave it exact for now, because now I'm going to cube root both sides to get b equals the cube root of 0.87 over 34. Now I'll plug that into the calculator and round to, let's say, 3 decimal places. And I am coming up with approximately 0.294. Let's see. Let's round that up to 0.295. So b, in this case a decay factor, is 0.295. And now coming up with the function is basically done. We just supply all of the defining components. We have our initial value, 34, and our base, our decay factor in this case, 0.295, to the x. So now that we've got our function, we can very easily plug that into the graphing calculator and use the table setting to calculate the rest of those outputs based on the inputs of 1, 2, 4, and 5. Alright, so if I type in 34 times 0.295 to the x, and I go to the table settings, I'd like to make sure that the table is set to auto this time, which mine currently is, and the reason for that is if I start at 0 and I have the calculator generate 1, 2, 3, 4, 5 for x, then I can just read down the right-hand column. So for x equals 0, y equals 34, check. For x equals 1, we get 10.03. Now, if we want 3 decimal places of accuracy, we might want to scroll over and see if that's as accurate as it gets, and 10.03 seems to be it. Then for x equals 2, we would get 2.959. And And for x equals 3, we get 0.87. It's a little bit off, but that's because we rounded here our base. So if we plug in 4, we get 0.257. And if we plug in 5, we get 0.076. So there's our table completed. We couldn't have done that without the function. Now, so far we have only really examined the situation where we know by what factor our amount is increasing. So we could say that something is doubling every year, or tripling, or increasing by a factor of 1.2 if it gets multiplied by 1.2 every year. But the other way we can express changes in amounts is by saying how much they increase. So right at the bottom of that page, definition 6.3 discusses the growth or decay rate. So far we've seen growth and decay factors, but in this situation, for example, in the question that we are looking at, we have an amount in a bank account, and we're told that it increases by 4% every year. We're not being told the factor, we're being told a rate of increase. So referring to that definition, if we think about how much money is going to be in the account after a year, in 2010, we're going to have 1,000 and 4% on top of that. So the way that we would describe the growth factor, B, that's going to be 1 plus our growth rate, R, where R is 4%. In other words, 0.04. So we always need to convert from percent into usable numbers, decimals. Alright, so we can conclude that B is going to be 1.04. That's the factor by which our money is being multiplied to determine how much will be left after a year. So after a year, we'll have $1,040. After 2 years, we're going to multiply 1,040 by 1.04, and that'll tell us how much we have in the account. So the other piece of the puzzle, our initial amount, the amount at time 0 is 1,000. So remember, 2009 is sort of our starting point. So 2009 is time 0. So our population function, or our exponential growth model, P of t, tells us how much money is in the account. We'll have 1,000 to start, and we're multiplying that by 1.04 every year. Okay? So if we do this once, our exponent would be 1, and we would multiply 1,000 by 1.04. If our exponent is 2, we'll multiply 1,000 by 1.04, and then we'll do it again to determine how much money is left after 2 years. Alright, so that is our setup when we are given the rate of increase. Now, if this were a rate of decrease, then our decay factor would have to be, is going to look a little bit different. So if we have a rate decrease, if we're losing money, then B is 1 minus R. In this case, where R still equals 4%, but this time we're losing 4%. So we have the 1 there to account for the money that we have, and then we're knocking off 4%, leaving us with 1 minus 0.04, or 0.96. In other words, we'll have 96% of our money because we're losing 4% of our money. So our model would look a little bit different. P of t would then be 1,000 times 0.96 to the t. And notice this would be decaying because b is less than 1. And that makes sense. If we're losing money, we should have a decaying function. Here, our b is greater than 1, and that reflects the growth taking place in the bank account. Now, the final strange topic in this section is that of changing time frames. So suppose here we have a colony of bacteria, and we begin with 60 organisms, so p sub 0 would be 60. We notice that the population quadruples every 2 weeks, but that might not be useful for us. Maybe we want to know about what's going to happen after week 3. Well, then knowing 2-week increments isn't as helpful. So what we might want to do is recognize what our base is going to be. Our base here, we're told that this population quadruples, so we're going to have a growth factor of 4. So I can begin setting up our equation. P of t is going to have the initial population times the base. Now we're going to be raising to a power. And, our base was actually 4. Let's put that in. So we're supposed to be raising to a power in such a way that 2 weeks in, we multiply by 4. 4 weeks in, we would multiply by 4 and then multiply by 4 again. So our exponent after 4 weeks should be 2. So I like to think of this as 2 separate quantities. What is our exponent going to be, and what is our time frame? Well, after 2 weeks, our exponent should be 1, right? That's 1 time frame. After 4 weeks, our exponent should be 2, right? We want to multiply by 4 twice, so we want to multiply by 16. After 6 weeks, our exponent should be 3. That's the 3rd time we check in. So what's the relationship here? Well, the exponent is going to be half the number of weeks. So if t represents the number of weeks, then our exponent should be t over 2. Right? After 1 week, our exponent should be a half. After 3 weeks, our exponent should be 3 halves. Right? And this, if this is t, then this is t over 2. Alright, well, let's see if this works. So our population after 0 weeks should be 60. So 60 times 4 to the 0 over 2. That's 60 times 4 to the 0. That's 60 times 1, which is 60, so we're good. Okay, our population is supposed to quadruple after 2 weeks, so we should have 4 times the original 60 after 2 weeks. So if we look at p of 2, that would be 60 times 4 to the 2 over 2. We'll simplify that exponent. That's 60 times 4 to the first, which is 60 times 4, which is 240. Exactly quadruple the original 60. Excellent. So it looks like we're in good shape, which means we could use this function to figure out how many bacteria there are after 5 weeks. That would be 60 times 4 to the 5 halves. That's something I would probably go ahead and plug into the calculator. So let's see what that works out to. If I type in 60, and I multiply that by 4 raised to the 5 halves, I get approximately 1920. Actually, it's not approximate, that's an exact number. So that's how many bacteria are in our population, or in our colony, after 5 weeks. So that's how you would handle the time frame. I like to think of what is my variable, and how is that related to the exponent, based on the situation that we were given in the setup. Well, that is all of the different topics out of this section. Go ahead and get started on those homework problems. Feel free to shoot me and ask your teacher, and bring any questions that you still have to class when we meet again.